Okay, in this section, we're going to finish the second part of our section 4.4 material on coordinate systems. So in the first part of this section, we had defined a coordinate mapping from a vector space into Rn by identifying a vector x with its coordinate vector relative to a basis for our vector space. So here, choosing a basis B consisting of vectors b1 through bn for a vector space introduces a coordinate system for that vector space, as we saw in the first part of this section. Now, the coordinate mapping, which is used to define that coordinate system, that is taking the vector x and giving a vector in Rn, called the coordinate vector for x relative to the basis b, connects the possibly unfamiliar space V to a more familiar space Rn. So visually, what this coordinate mapping is doing is taking an abstract vector space V, where we have vectors within that space x, and it is mapping them. So here our coordinate mapping, we might call this coordinate vector associated with the vector x relative to the basis b, and it is giving us a vector in Rn. Now Rn can be visualized using an orthogonal set of vectors, or standard set of vectors. Here maybe we'll draw it in x1, x2, x3 space. So we have associated some coordinate vector of x relative to the basis b, whose coordinates are given in terms of x1, x2, and x3. All right. So this coordinate mapping is useful in thinking about an abstract vector space in relation to the more familiar vector space Rn. So our next result, theorem 4.8, will give us a little bit of information about this coordinate mapping. So if we have a basis B consisting of n vectors for a vector space V, then this coordinate mapping from x to the coordinate vector of x relative to b is a one-to-one linear transformation from the vector space V onto Rn. All right. So in order to show that this mapping is linear, we need to show that it preserves vector addition or scalar multiplication. So here, let us consider two vectors in our vector space V. So let's call these vectors maybe u and w. Now, since B is a basis for the vector space V, that means that each of these vectors is some linear combination of our basis vectors. Say C1 times B1 plus C2 B2 up through Cn Bn. And a different vector W might have a different linear combination representation with weights, say, d1 through dn for these basis vectors. Now, if we want to show that this transformation preserves vector addition, let's consider the sum of these two vectors, u and w. So here we would have the vector c1 plus d1 times b1 plus c2 plus d2 times b2 up through cn plus dn times bn. So it follows that the coordinate vector of this sum, u plus w, relative to the basis b, would have entries given by these weights. So our first coordinate would be the sum of C1 and D1 up through our nth coordinate, Cn plus Dn. So we have C1 plus D1 up through Cn plus Dn as our associated vector in Rn. But of course this vector can be decomposed as the vector C1 through Cn plus D1 through Dn, which is exactly the sum of the coordinate vectors of u and w relative to this basis b, because the weights for the vector u were c1 through cn, the weights for w relative to our basis were d1 through dn. So these two vectors are exactly the coordinate vectors for u and w relative to the basis b. So we see the mapping of the sum of the vectors is the sum of the mappings of those vectors. Now we still need to show for linearity that this preserves scalar multiplication. So let us consider a scalar, say r, and let's consider the vector r times u. So that is r times u, which was c1, b1, up through cn, bn. So distributing our constant r, we would have rc1 times b1 plus rc2 times b2 up through rcn times bn. So it follows that the coordinate vector for r times u with respect or relative to the basis b is the vector rc1 through rcn. We have those as the weights for this linear combination of the vector ru. But of course, we could think of this as the scalar r times the vector c1 through cn, which would be exactly r times the coordinate vector of u relative to the basis b. So we've shown that this transformation preserves vector addition and preserves scalar multiplication, so this mapping must be linear. So here we can say thus, the mapping is linear. Now the remainder of that theorem is to prove that this mapping is also one-to-one and onto, which are exercises in your textbook left as homework. So if you follow through those exercises, you can establish the remainder of this theorem, namely that this is a one-to-one and onto linear transformation. Okay. So the linearity of this transformation, that is the coordinate mapping, extends to arbitrary linear combinations of vectors. So that is, if we have a set of p vectors, u1 through up in a vector space with scalars c1 through cp, then the coordinate mapping of a linear combination of those vectors is the linear combination of the coordinate mapping of the vectors u1 through up. Okay. Now, this coordinate mapping that we're talking about in Theorem 4.8 is an example of what's called an isomorphism from V onto R. So what exactly is an isomorphism? Well, in general, a one-to-one linear transformation from a vector space V onto a vector space W is called an isomorphism from V onto W. So even if we have different notation and terminology for vectors in V and W, we can think of those two vector spaces as being indistinguishable as vector spaces if there's an isomorphism between them. So that is, we can represent every vector space calculation in our space V in terms of a vector calculation in the vector space W or vice versa. So where this comes into play for our course is that any real vector space which has a basis of n vectors, using our coordinate mapping, we can show that that vector space is isomorphic to Rn and is therefore indistinguishable from Rn. So all of the theory for vectors or vector spaces that we have associated with Rn can be thought of in terms of the vector space V, or more importantly, we can take vectors in maybe an abstract vector space V and think about associated calculations in the vector space Rn, which we're more familiar with. So as an example of this, let's consider the following problem. Suppose that we're working with the space of polynomials, and we take B as the set of polynomials 1, t, t squared, and t cubed, which is the standard basis for the space P3, that is, polynomials of degree 3 or less. Now, any typical vector P within the space P3 can be written in the following form. So P of t, a general polynomial of degree 3, could be expressed as a0 plus a1 times t plus a2 times t squared plus a3 times t cubed. So here we are asked to find the coordinate vector of that polynomial relative to this basis B. So here we've almost immediately got our coordinate vector. We see that this polynomial, P of t, is a linear combination a0 times 1 plus a1 times t plus a2 t squared plus a3 times t cubed, where 1, t, t squared, and t cubed were our basis vectors for that space. So our coordinate vector of this vector P, or our polynomial P, relative to the basis B, would be the vector in R4 whose entries are these weights, a0, a1, a2, and a3. So here, this is a vector in R, where n is equal to 4. So we can see that our space P3 of degree of polynomials degree 3 or less is isomorphic to R4. So any operation that we're performing in this space P3, we can associate with some vector operation in R4. And we're more familiar, or we're more comfortable working with vectors in R4 than we are vectors in polynomial space. So to show some applications, let's consider the following. Here, suppose that we have the following set B, consisting of these 3 polynomials, and we're told that this is a basis for P2, the set of all polynomials degree 2 or less. So for that basis, we want to find the coordinate vector of this polynomial relative to that basis. So just like we did in our examples earlier in this section, the basis coordinates of this polynomial P of t satisfy the following equation. If we take the first coordinate, let's call it C1, times our first basis vector, which is the polynomial 1 minus t squared, plus the second coordinate, c2, times our second basis vector, t minus t squared, plus c3 times our third basis vector, which was 2 minus 2t plus t squared. We should be getting back the polynomial p, which was 3 plus t minus 6t squared. So we need to solve this equation for those coordinates. So if we were to expand this left-hand side and group our coordinates according to powers of t, well, let's start with our constant coordinate. So we would have 1c1 plus 2 times c3 for our constant. So here we've got our 1c1, the second term didn't have any constants, and then 2 times c3. Now expanding and grouping terms involving t to the first, we would have 1c2 times t to the first minus 2c3 times t to the first. For this term and this term, and our first basis polynomial didn't have any t to the first term. So then for our t squared term, well, we're going to have negative 1 c1 t squared minus 1 c2 t squared plus c3 t squared. So our coefficient for t squared is negative c1 minus c2 plus c3. And this has to equal the polynomial 3 plus t minus 6t squared. So in order for these two polynomials to equal each other, for all values of t, we can equate their coefficients. So here, equating the coefficients, we have a system of linear equations. So equating the constant coefficients, we have 1 c1 plus 2 times c3 is equal to the constant 3. The t coefficients give us 1 c2 minus 2 c3 is equal to 1 times t. And then our t squared coefficients give us negative c1 minus c2 plus c3 is equal to negative 6. So we need to solve this system for c1, c2, and c3, which we can do by making use of an augmented matrix. So here as an augmented matrix, we can express this in the form 1, 0, 2, 3, 0, 1, negative 2, 1, and negative 1, negative 1, 1, negative 6. All right. So performing row reduction, we can solve for our constants. So here, using the 1 as the lead entry in my first row, I'm going to eliminate the negative 1 in my third row by taking row 3 and adding row 1, which gives me a first row of 1, 0, 2, 3, second row 0, 1, negative 2, 1, and then summing the first and the third row, I have 0, negative 1, 3, negative 3. All right. So my first column is exactly as I want. I have a 1 in the first row, zeros below it. In my second row, I have a leading 1, which I can use to eliminate the negative 1 below it by taking row, see if I can squeeze this in, row 3 plus row 2. So my first row is 1, 0, 2, 3. Maybe a little too tight here. Let me use a new line. Taking row 3 plus row 2, my first row remains 1, 0, 2, 3. My second row is 0, 1, negative 2, 1. And my third row becomes 0, 0, 1, negative 2. All right. So we're almost done. I need one more step where I'm going to use the 1 as the leading coefficient in our third row to kill off the negative 2 and positive 2 that appear above it. So here, if I take row 1 minus 2 times row 3, or row 2 plus 2 times row 3, I have a first row of 1, 0, 0, 7. Second row of 0, 1, 0, and negative 3. And my last row is 0, 0, 1, negative 2. So these values are the coefficients C1, C2, and C3 of our polynomial relative to this basis. So the coordinate vector of P relative to the indicated basis is the vector 7, negative 3, negative 2 in Rn. All right. So let's look at another one. In this next example, we have a set of 3 polynomials, and we're asked to use coordinate vectors to test the linear independence of these polynomials. So for linear independence of polynomials, well, it can be a little bit difficult to establish in the space of polynomials, but we know how to establish linear independence of vectors in Rn pretty easily. So let us think about finding coordinate vectors for each of these 3 polynomials using probably the standard basis for this set of third degree polynomials, and then see whether those associated vectors in Rn are linearly independent, because if they are, then these 3 polynomials must be linearly independent in their vector space. So here, let us start by finding the coordinate vectors for these 3 polynomials, P1, P2, and P3, relative to the standard basis. Which for polynomials of degree 3 or less would be 1, t, t squared, and t cubed. So here, these coordinate vectors that I'm looking for are the following. So the coordinate vector for P1 with this basis B would be given by, well, we have P1 is 1. We have 0 t terms. We have negative 2 for the coefficient of t squared and negative 1 for the coefficient of t cubed. Now the coordinate vector for P2, well, we have 0 for our constant. We have 1t, 0t squared, and 2t cubed. And then the coordinate vector for P3 relative to this basis is we have 1t squared, or 1 times t, 0 t squareds, and negative 2t cubed. All right. So we need to determine whether these 3 coordinate vectors are linearly independent in R4. So to determine linear independence for a set of vectors, well, there's a few ways we could do this. So writing these vectors in the columns of a matrix A, we have the following. Our matrix A would be 1, 0, negative 2, negative 1, 0, 1, 0, 2, and 1, 1, 0, negative 2. Now, if this were a square matrix, which it is not, this was 4 by 3, we could use the determinant to determine whether our column vectors were linearly independent by using the invertible matrix theorem. However, this is not a square matrix, so the invertible matrix theorem does not hold here. But to determine whether these vectors are linearly independent, we want to see whether the equation ax equals to 0 has non-trivial solutions. So augmenting this matrix with our 0 vector, let's see if we have only the trivial solution or non-trivial solutions. So here to perform row reduction, we could take first off row 4 plus row 1, or row 3 plus 2 times row 1, which makes my first row 1, 0, 1, 0, so leaving it alone here. Our second row, I'm going to leave alone 0, 1, 1, 0. Now for our third row, we will have 0, 0, 2, 0. And our third row, our fourth row, excuse me, performing this operation, we have 0, 2, negative 1, 0. All right. So now let's take row 4 minus 2 times row 2. So our first row will still be 1, 0, 1, 0. Our second row is still 0, 1, 1, 0. Our third row, we could simplify as well in the step by taking half of row 3, so we have 0, 0, 1, 0. And performing the indicated operation on row 4, we have 0, negative 2 plus 2 is 0, negative 2 minus 1 is negative 3, and 0. So now using this pivot of 1 in my third row, I can eliminate all of the entries in that third column by taking, for instance, row 1 minus row 3, row 2 minus row 3, or row 4 plus 3 times row 3. And this gives me 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and a row of all zeros. So since our matrix has a pivot in each column, we know that this set of vectors is linearly independent. Another way we can think of this is the linear combination of these vectors set equal to 0 has only the trivial solution where each of those weights is 0 using the 3 rows of this augmented matrix. So here the vectors, these coordinate vectors, P1, P2, and P3 relative to the basis B are linearly independent, but because this coordinate mapping is an isomorphism, the same result holds for the space of polynomials. So we can say that the polynomials P1, P2, and P3 are linearly independent in the space P3. All right. So in our last example for this section, we are given vectors v1, v2, and x, and we're told to let B, the set of v1 and v2, be a basis for the span of v1 and v2, which we're calling a set H. And we're asking if x is in H, and if it is, what are the coordinate vectors for x relative to that basis. So here, let's see if we can determine if x is in H. So we'll say here, x is in H, which was defined as the span of the vectors v1 and v2. If x can be written as a linear combination of those vectors, something of the form c1v1 plus c2v2. So writing this in terms of a augmented matrix, we would have, or maybe in terms of vectors first, we have x, which was 3, 12, 7, has to equal c1 times v1, 3, 6, 2, plus c2 times v2, which was negative 1, 0, 1. So writing this vector equation as an augmented matrix, let's say consider an augmented matrix. Where our coefficient matrix would be the matrix 3, 6, 2, negative 1, 0, 1. And we're augmenting that with the vector x, which was 3, 12, 7. All right. So performing row reduction, we can simplify. So I know I want the leading entry in our first row to be a 1 instead of a 3. So one way I could get it is using the 2 from my third row and subtract that from my first row. So that is row 1 minus row 3, which makes my first row 1, negative 2, and 3 minus 7 is negative 4. Our second row, we can eliminate the leading 6 by taking row 2 minus twice row 1. So we have negative 6 plus 6 is 0, 2 plus 0 is 2, and negative 6 plus 12 is 6. And then in our third row, we could take a, let's leave it alone for now. We'll write it as 2, 1, 7. Okay. So now, using this leading 1, I can eliminate the 2 that appears in that third row by taking row 3 minus twice row 1, which makes my third row negative 2 plus 2 is 0, 4 plus 1 would be 5, and then 8 plus 7 is 15. In our second row, I could multiply through by a 1/2, which would give me 0, 1, 3. And my first row I'm going to leave alone, 1, negative 2, negative 4. So now, using the 1 as the leading entry in my second row, I can eliminate the 5 and negative 2 that appear above this by taking row 1 plus twice row 2, or row 3 minus 5 times row 2. So my first row becomes 1, 0, 2. My second row is 0, 1, 3. And my last row becomes 0, 0, 0. So we find that the coefficients for this vector x relative to the basis b are 2 and 3. So we've established that x is an element of H, and the coordinate vector for x relative to this basis b is the vector 2, 3. All right. So this last example illustrating that the span of a set of two vectors in space is isomorphic to the real plane R2.